Good morning, students. Please turn to page 273, read through 10.1 warm-up, hit pause, and then we'll go through the answers here. All right, now that you had a chance to try it, number one, how are the two coin stacks different from each other? Well, first off, both stacks form two different kinds of solids. Depending on how we slice a vertical cross-section may have different in appearance. If I went right off to the edge, it would be kind of a tall, skinny rectangle. And if I did it roughly in the same spot here, that cross-section would not be a rectangle. It would kind of look like an interesting half ellipse. Number two, does either stack of coins resemble a geometric solid? If so, which stack and what solid? Well, stack A is what we call a right cylinder because the base on the bottom, which is congruent to the base up top, is directly stacked right up above it. It is a direct dilation, vertically or perpendicular. And if you notice here in part B, that is called an oblique cylinder. It's when the base is translated not perpendicularly, but translated at maybe a slight angle. We'll explore those two kinds of shapes later on in the unit. Number three, how do the heights compare? Well, they both have the same amount of quarters, and they're stacked upon each other, so therefore the heights are the same. And how do the volumes compare? Well, they have the same volume. The reason why is each stack has a quarter as its base, which means the area of that base is the same for figure A and figure B. Since they have the same heights, the area of the base times the height would give me the same volume for both shapes. All right, you don't have to write this down unless you want to. If you want to, you can go ahead and hit pause. We're going to look at the definition of a right solid. A right solid is referring to a prism or cylinder that is said to be right when one of the bases is translated or coincides with the other. The directional line segment that defines the translation is perpendicular to the base. So when we talk about that word right, I think 90 degrees, and the reason why is the line connecting them. If I connected here on the pentagonal prism, if I translated the bottom directly up to the top and followed the direct line segment, that would be a perpendicular, which would make reference to the 90-degree angle. If I have a cone, and a cone is a line is drawn from the apex, remember the apex is the top. If I go straight down to the base, if that forms a 90-degree angle with the base, then that is considered to be a right cone. And same thing with a pyramid. Here from the apex, straight down to the base, has the perpendicular line that goes right through it. And that's how we're going to be defining a right prism and right pyramids. So oblique, this might be the new one for you. Prisms and cylinders are said to be oblique. When one of the bases is translated to coincide with the other, the directed line segment that defines the translation is not perpendicular. So here you can see if there was a line drawn, in this case you really wouldn't need the line, but notice this line here that connects the bottom base to the top is a different angle. It is not 90 degrees. We don't actually know what that angle is. If it is a pyramid or a cone, notice what we're actually doing is, this is called the altitude. The height of the solid is not inside of the base, and if I was to translate the apex on down, it would be translated by a non-perpendicular line segment. So, quick way to think of it, if the solid stands straight up, it's right. If it slants a little bit, like a stack of quarters that's being pushed over, that's considered an oblique solid. So we're going to look at activity 10.2 on page 274. To help get your thinking right, we're going to look at a stack of note cards. So picture a stack of note cards, like in the picture shown here. What kind of geometric solid does the stack of cards resemble? What is the shape of the base? What is the shape of any cross-section that's taken parallel to the base? And if the stack is shifted to create an oblique prism, what does the shape of the base change? Does the shape of the cross sections change? We're going to explore all that with this next activity. So what you have on the top of page 274 is an image that shows two rectangular prisms. Think of them as like the stack of note cards. All right, so we have the stack of note cards in blue, and in green we've got the stack of note cards that was just slightly tilted over to create an oblique prism. The bases of the prisms are congruent. Each base has an area of b square units, and the prisms have the same height. A plane intersects the two prisms parallel to the base, creating cross sections. You can kind of see the cross sections highlighted here. So use that image to answer questions 1, 2, 3, and we'll go over the answers shortly. Press pause and then hit play when you're ready. For number 1, we're going to look at the cross sections. Well, think of this. If these are both stacks of paper, stacks of note cards, and one of them is stacked perpendicularly, straight up and down, and the other one is just tipped over slightly, and I pull a flat piece out, a cross section out, picture it just being one note card that has 0 width, it would still be a note card. The actual shape of the cross section doesn't change if the stacks tilt slightly over. So in this case, both prisms will have the same cross section, which would be a rectangle. It would be the shape of exactly one of those note cards, right? And that'd be true for each one. How would the shape or the area of the cross sections change if we move the plane up and down? So if I moved up and down vertically parallel to the base, that would be just like selecting a different note card in the order of the stack. There would be no change. It would still be a rectangular cross section with the exact same area. So then that means that no matter where I'm at on either stack, the cross-sectional area from all the way down to the top, all the way up to the bottom, would be equal. Right? Every single one of them would be the exact same shape, size, and have the same area. So, how do we know the volumes, or how do the volumes of the two prisms compare? If they have the exact same cross-sectional area and the exact same height, then the volumes would have to be the same. So they have the same volumes since the area of the bases are congruent and the heights are congruent. Our volume formula from last unit would come into play. Let's look at a quick applet here, just to kind of get a feel for what they're trying to explain. And notice here, if I move the base, here you can see that if I move the base, these two shapes have the exact same base. If I change the skew, that makes it more oblique. And then I can actually take the plane, and the plane is just moving parallel to the base, but notice, no matter how I move it, you can see that those cross sections, if I move it back over, see how that cross-sectional area is still the same? Even if it's tilted, that area still stays the same. And it's true all the way from the top on down to the bottom. It has the same area of cross-section throughout. Alright, that leads us to Cavalry's principle. This is on your blue reference sheet. I believe it is Unit 5, Lesson 10 on the top of the page. It says, if two solids are cut into cross-sections by parallel planes, and the corresponding cross-sections on each plane always have the same area, then the two solids have to have the same volume. So here, even if they're different shapes, if they have the same cross-sectional area and the exact same height, then the volumes will be equal. So go ahead and annotate this when you're ready. You can hit pause when you're ready. Hit play. We're going to go to page 275. This is activity 10.3, equal volumes. For each pairing of solid, decide whether the volume of the two solids are equal. Explain your reasoning. If you and your partner disagree, discuss each other's approach until you reach an agreement. I'm going to actually have you go through all 6 of these. It spans on to page 276. So go through 1 through 6 and decide if they have the same volumes or not? We'll go over the answers shortly. Let's look at number 1. So what we're looking for here is, in order to have the exact same volume, I need to have the area of the base and the height be the same for both solids. And that base, the cross-sectional area, has to be consistent throughout the whole shape due to Cavalry's principle. So if you look at number 1, they gave us the area of the base is 12 and the height is 6. For the second solid, we get to pick our base. I'm going to pick the base on the bottom because 3 times 4 is 12. So I have the same area of the base and the height is also 6. So these two solids would have the same volume because of our logic right here. Same area of the base, same height. So let's look at number 2. Number 2, notice right away we have different heights. The height of the right cylinder is 10. The height of the oblique cylinder is 7. So right away, even though they have the same area of the base and the cross-sectional area is the same all the way through, they have different heights, so therefore the solids would not have the same volume. Now be careful, this 10 is not the height on the oblique solid. That's just the distance between the bases. The height is always indicated by a perpendicular. All right, number 3. Notice the area of the base for each cone is pi times radius squared, so pi times 3 squared, or 9 pi. So here we have the same area of the base, and then we have to look at the height. The height for a right cone is indicated from the center of the circle through the apex at a perpendicular, and the height for the oblique cone is from the apex straight down to where the base could be, or the plane that the base is on. Both of those heights are 5, therefore same area of base, same height, so we have the same volume. Number 4. Now this one always tends to trick people. Here we have what's called a right triangular prism. Notice it's a right triangle all the way throughout, stacked left to right. So its base is 3 by 4, and then we're cutting it in half because it's a rectangle. Triangle. So its area of the base is 6 units. The height is not how tall the item is, it's what's the distance between the bases, so the height would be 5. So area of the base times the height would give us the volume. Then I'll go to the rectangular prism. I get to pick the base. I'm going to choose the base that has the same area of the base as the triangular prism. So I'm going to go 1 by 6, calculate the area. The area of the base is 6. It is a height of 5, so yes, the volumes are the same because the area of the bases are the same and the heights are the same. Notice how we're using Cavalieri's principle to help us solve this. Let's look at number 5 really quick. So notice the base for the triangular, actually this is rectangular pyramid. The base is 5 by 5, which is 25, and the height is the distance from the base to the apex at a perpendicular. So that height is 5. And this one's kind of an oddly shaped rectangular prism pyramid. Notice in the back we've got 2 right angles. That means this back dotted line is going straight up and down through the apex. So the height of this solid is 5. It has a base, 5 by 5 square, that is 25. So we have the same base and the same height. So yes, these two solids would have the same volume. And then we have our last one. Notice right away these are 2 different shapes. They do have the same area of the base. The heights are the same. However, the cylinder has a circular base throughout that remains the exact same area all the way through from top to bottom. The cone, the cross-sectional area from the apex on down is going to change. It's going to be small up here and get bigger and bigger and bigger. Since the cross-sectional area is not consistent for the cone, the volumes could not be congruent. Even though they have the same area of the base and the same height, we have to keep in mind that that cross-sectional area has to be consistent. All right, we're going to add this to your blue sheet. This is our last theorem for the day. It says, a prism or a cylinder whose base has the area of b square units and whose height is h units has a volume of area of the base times the height, cubic units, regardless of the shape of the base or whether the solid is right or oblique. So as long as you know the area of the base is consistent throughout and you know the height, you can calculate the volume. All right, annotate, and then when you're ready, press play, and we're going to move on to Lesson 11. Go to page 282, and what you're going to do is, without doing any calculations, identify two solids that you think would have the least difficult volumes to calculate, and two solids that would have the most difficult volume to calculate. Be prepared to explain your reasoning. So go ahead and hit pause and look through the list of solids and select two easy ones and two hard ones. All right, now that you've chose those, I'd like you to choose three of the solids, one from your least difficult list, one from your most difficult list, and then pick one other ones that you did not choose. So you got to do three different ones, round your answers to the nearest tenth. We're going to go over the answers here shortly, and I'll have my calculations next to it. Press pause, work through this, and hit play when you're done. So you may have picked different ones than I picked. I'm actually going to show all the answers, and I'll talk through a couple. For part A, we have a triangular base. It's the same base from top to bottom. So the area of that triangle is 11 times 5 times 1/2. 1/2 base times height. And then the height would be 8. So 55 halves times 8 would give me 220 centimeters cubed for the volume. Part B is one of the trickier ones. My guess is you might have picked that as one of the more challenging ones. Notice we have the angle of 40 degrees. Well, if I was to draw a dotted line to represent the height of the oblique cylinder, that would form a right triangle with the length of 10 for the hypotenuse and an angle of 40 for my reference angle, and then x would be the height of the solid. So I just redrew that triangle over here, and now this is a SOHCAHTOA problem. It's a trig problem. I have to find x, which is in the opposite spot. I know the hypotenuse is 10 and the angle is 40 degrees. So opposite and hypotenuse would be the sine function. Sine of 40 equals x over 10. I'm going to times both sides by 10 to get x by itself. That would tell me the height, using my calculator, is 6.428. The area of the base then, I actually didn't write it out how I found it. The area of the base is pi r squared. The radius is 5. 5 squared is 25 times pi. And then when I multiply those together, I get 504.844 units cubed. For part C, I decided to switch it up, and maybe I did it a little different than you did. Notice how I called the front face the base. So that would give me a area of a base of 7 times 10, or 70. And then that would leave the height to be the distance between the bases of 5. The area of the base times the height, 70 times 5, should be 350 feet cubed. If you did the bottom as the base, you would have got 35 times 10, which is the same answer. If you chose D, this one required a little bit more work. You can see the base is a triangle. We know one leg and one hypotenuse of a right triangle. So the first thing you need to do, I just redrew the base here. I have to find the other length using Pythagorean Theorem. So c squared equals a squared plus b squared. When you solve, you get the square root of 15 for this other side length. Now we can find the area of the base by doing the length times width divided by 2. And that will give me the area of the base, which leaves the height to be the distance between the bases of 11. And when you multiply that together, you get a volume of 149.110 meters cubed. All right, part E. Maybe that was one of the friendlier ones for you. They give us the radius and they give us the height. The area of the base is the radius squared times pi. So I left my answer as an exact answer. 400 pi is the area of one of the bases. The height is 15, so we'll multiply those together. Your exact answer would be 6,000 pi inches cubed. If I did 6,000 times the pi button, I got 18,849.556 inches cubed. All right, part F. This one, notice the base is a right triangle, and it has a 30-degree angle, and we know one side length. Now, you could use SOHCAHTOA here. I decided, because it's a 30, 60, 90 right triangle, I decided to use our special formula where across from the 30 was x, across from the 90 is 2x, leaving the angle, or the side length across from the 60 has to equal x times the square root of 3. Well, here, 4 equals x squared of 3. If I divide both sides by the square root of 3, I get 4 over square root of 3, and that will leave me with this side length of the right triangle. Now, if you wrote that as a decimal, which you would get a decimal answer by SOHCAHTOA, it should be equivalent to 4 over square root of 3. Now, the area of the base. 1/2 base times height, so 1/2 4 times 4 over square root of 3. I multiply that all in my calculator. I ended up with 8 square root of 3, or 4.619 for the area of the base. We'll multiply that by the height, which is the distance between the two triangles, at 6.5. And you should have got a volume of 30.022 centimeters cubed. All right, next one. This one's kind of an interesting one as well. Notice they give me the height of an oblique cylinder, and then they give me the circumference. Circumference is the distance around the base. Well, I need to use that to find the radius, so I'm going to actually work backwards. I know the circumference is 4. I know the circumference formula is 2 pi r. So 4 equals 2 pi r. I'm going to divide both sides by 2. And that'll leave me, notice 4 divided by 2 is 2, and leave the pi on the bottom. So my radius is 2 pi. You could use that as a decimal if you want. I would recommend rounding to 3 decimals. And then we're going to use the fact that we know the area now. We know the radius. We're going to actually take that and plug it into the radius for the area of the circle. Area of the circle is pi r squared. So if I square 2 pi, I'm going to square the top and the bottom. I get 4 over pi squared. Notice I'm going to multiply that by pi. A pi on top and a pi on bottom will cancel, leaving me with 4 pi. Or if you just use your calculator, you get 1.273. Now I know the area of the base. The height is the perpendicular distance from the base to the other base, so 2 meters. So I'll take the area of the base of 4 pi times 2 over 1. 4 times 2 is 8. Pi times 1 is pi. 8 pi meters cubed is the exact volume. 2.546 meters cubed is the estimated volume. All right, so let's think about this. What measurements do we need to calculate volumes? Well, for rectangular prisms, you need length, width, and height. Prisms with triangular bases, the area of the base is 1/2 base times height of any triangle, and usually they give you some kind of right triangle. You need a base and a height to find the area of that one. For cylinders, if your base is a circle, pretend that's a circle, the area of the base is pi r squared, so you need the radius. Under what conditions are the Pythagorean Theorem and trigonometry used? Well, anytime you're given a right triangle, you could use Pythagorean Theorem if you know 2 sides of the right triangle. Trigonometry is used when we have an acute angle given. We're not going to do inverse trig very often on this one because we're looking for side lengths when working with volume. We don't really need to know angles. So most likely they'd give you an acute angle theta, and you would use SOHCAHTOA to determine any missing side length. All right, if you guys would, today you're going to do the lesson 10 summary, annotate that on page 277, complete 1 through 8 practice problems, and then do the lesson 12 summary on page 285, complete the problems 1 through 9 for Lesson 11. Remember to check solutions online. Keep plugging away at Delta Math. That's due on Friday. And then if you have time, you can do corrections for full credit back on your quiz. All right, have a good one. Adios.